Welcome everyone. In this video, I'll be covering section 11.6 on absolute convergence and the ratio and root test. So we have been seeing so far a sequences, series and different types of series, telescoping series, geometric series, um, a P series, harmonic series, and we have seen what are the conditions under which these series are convergent or divergent. Then we have seen few tests to check whether the series is convergent or divergent. Certain tests are applied only to series of positive terms. So we have seen integral test, comparison test, limit comparison test along those lines. And then we have seen also series which are alternatively positive and negative, which have alternatively positive and negative terms, which is called alternating series. Then whenever you recognize a series as an alternating series, you will apply alternating series test. So it has got certain requirements, and then you apply those, verify those conditions, and then you decide whether it is convergent, whether the series is convergent or divergent. So uh, next along those lines, we are going to see when the series is said to be absolutely convergent, and what are these ratio and root tests. The given any series sigma an, we can consider the corresponding series by considering the absolute values of all the terms. Mean that you are making the series all positive terms. So absolute A1, absolute A2, absolute A3. So you are taking absolute values of all the terms of the series, whose terms are all absolute values of the terms of the original series. A series sigma an is called absolutely convergent if the series of absolute values, namely sigma absolute an, is convergent. If sigma absolute an is convergent, meaning if you take the absolute values of all the terms of the series and if that series is convergent, then the original series is said to be absolutely convergent. Notice that if sigma an is a series with positive terms, if all are positive terms, there is no difference between saying sigma an versus sigma absolute an, because absolute an would be the same as an. So the absolute convergence is the same as convergence in that case. There is no need to say absolute convergence. Now let's take this series, the series sigma negative 1 to the power n minus 1 over n square. If you substitute values n equal to 1 through infinity, then you get 1 minus 1 over 2 square plus 1 over 3 square minus 1 over 4 square, etc. And this series is absolutely convergent. It's absolutely convergent. Why? If you take absolute values of all the terms and make a series, you will be having sigma negative 1 to the power n minus 1, absolute value of that divided by n square. The absolute, you know that absolute negative 1 to the power n minus 1 is after all positive 1 or negative 1 as we vary the values of n. So it will be just plus or minus 1 without the absolute. But when you take the absolute value, all are going to be positive 1. So it's going to be sigma 1 over n square. So what do you know about sigma 1 over n square? This is nothing but a p series with p equal to 2 more than 1. So it is definitely a convergent one. So you notice that sigma absolute an is convergent. That is equivalent to saying sigma an is absolutely convergent. But the alternating harmonic series, which is sigma n varying from 1 through infinity, negative 1 to the power n minus 1 over n, if you substitute values of n successively starting from 1, you get these alternating series 1 minus 1 half plus 1 third minus 1 fourth, etc. This is nothing but the harmonic series, except that you're having the numerical values of the terms, the positive part of each of these terms are nothing but the harmonic series terms, but here you have alternatively positive and negative terms. So in this one, if you apply alternating series test, this would be convergent. The series would be convergent by alternating series test, but it is not absolutely convergent. It's not absolutely convergent. So let's prove this. Let's prove this part. Yeah, we are going to consider the alternating series. That alternating harmonic series is convergent, but not absolutely convergent. So this, let's consider negative 1 to the power n minus 1 over n. If we expand, it's 1 minus 1 half plus 1 third minus 1 fourth. So it is an alternating series. This is an alternating series. So apply alternating series test. Apply alternating series test. So we need two conditions. So Bn plus 1 less than or equal to Bn. So let's consider sigma absolute An, which is sigma Bn, which will be sigma 1 over n. We know that 1 over n plus 1 is less than 1 over n. In other words, Bn plus 1 is less than or equal to Bn, which is condition 1. Then limit as n approaching infinity of Bn is limit as n approaching infinity of 1 over n, which is equal to 0, which is condition 2. Both are satisfied. Therefore, by alternating series test, you can conclude that sigma negative 1 to the power n minus 1 over n is convergent. So when you write sigma, it's assumed that it's sigma from n varying from 1 through infinity. So we got the first part done. So it is convergent part is done. So we have to prove that it is not absolutely convergent, right? So to prove, sigma negative 1 to the power n minus 1 over n is not absolutely convergent. So consider absolute value of an, which is sigma absolute of negative 1 to the power n minus 1 over n. As this negative 1 to the power n minus 1 is only plus or minus 1, when you take the absolute value of it, it will be just sigma 1 over n, which is the harmonic series. Or you can say either way, P series, it P equal to 1. In either case, it is a divergent one. So that proves that it's not absolutely convergent. It is not absolutely convergent. So this proves that sigma -1 to the power n minus 1 over n is not absolutely convergent. So we have shown two things. We have shown that the series is, this alternating harmonic series is convergent, but the alternating harmonic series is not absolutely convergent. Such a series is said to be conditionally convergent. It is convergent, but not absolutely convergent. A series sigma an is called conditionally convergent if it is convergent but not absolutely convergent. Thus, the above alternating harmonic series is an example of a conditionally convergent series. Theorem: if a series sigma an is absolutely convergent, it is automatically convergent. A series which is absolutely convergent is automatically convergent. We can prove this easily. So if you consider this inequality, consider this inequality, 0 less than or equal to an plus absolute an, which is less than or equal to, so each one is, any value is less than or equal to its absolute value, correct? So an is less than or equal to absolute an, and then there is also another absolute an existing. So we get 0 less than or equal to an plus absolute an, which is less than or equal to twice absolute an. So sigma an is given to be absolutely convergent. It's given that sigma an is absolutely convergent. What does it mean? Sigma absolute an is convergent. That's the meaning. If you take absolute values of the terms, it is convergent. And therefore, the right hand side, 2 times absolute an is also convergent. Two times absolute an is also convergent. So we notice that sigma an plus absolute an is convergent by comparison test. By comparison test, sigma an plus absolute an is convergent. So if you take an with sigma an, so I have to write sigma here, sigma an plus absolute an is convergent by comparison test. Here we are taking one term, so we have taken the nth term of the comparing series and with the nth term of the given series. So we have sigma an equal to sigma an plus absolute an. We can write like this. It's just adding and subtracting sigma absolute an. Kind. Each one of these terms is convergent. So you have a convergent one here. This is a convergent series. This is also a convergent one. Therefore, it is difference of two convergent series and therefore convergent. So if a series sigma an is absolutely convergent, then it is automatically convergent.